So today we're going to be talking about the network layer. This is our first unit in a series of units that we're going to talk about the network layer, but this is the first time we've talked about protocols that are not going to be implemented just on the edge network. So far it's only been the edge network. The application layer, the transport layer, they've all been on the edge, just at the host or the server or whatever. Now we're starting to dive into the core of the network. So it's really exciting. There's two parts to the network layer. There's the control plane and data plane. We'll define what those are in a second, but this series of lectures is going to be on the control plane, and then we'll move and spend like one or two, I think just one lecture on the control plane. So today we're going to talk about the control plane, data plane, what that means, and kind of give a high-level overview of the network layer. Then we're going to talk about what's inside a router, just how it all works. Next lecture we'll cover IP, the internet protocol, the actual like the headers and addressing. There's a lot of interesting things here. IPv6, how people get IP addresses, and that will be it for the data plane. And then, like I said, we'll cover the control plane afterwards. So what services does the network layer provide? So here we got this picture. You should be familiar with it. We got our end hosts, the core of the network. So far, like I said, we've only been talking about these edge devices right here. So some laptop wanting to talk to some server somewhere. So what is the job of the network layer on those devices? Their job is like pretty much every other layer we've talked about so far. They take data from the layer above. So in this case, take data from the transport layer, they encapsulate it into a segment, and then they pass it to the link layer, the layer below it. And on the receiving end, it does the reverse. It receives the data from the link layer, breaks it apart, looks at the header, makes sure it's takes care of all the stuff it needs to, and then passes up to the transport layer. So that's what the end device is doing. But now, because the network layer is implemented on all devices in the network, we now have to worry about, well, what's happening in between here? What does a router do with this data? Because now before it didn't know anything about transport layer. So if it got something transport layer related, that's not possible. It doesn't know even how to handle transport layer. Everything is encapsulated into a network layer packet. So now we will talk about, well, what do these routers do? They do things like examine the header of this network port, and that will help them decide, do I, if I'm right here, do I send it to this node right here, or do I send it to this node right here, or do I do something else with it? And that's through examining the headers. And that helps it get from one point right here, where so far it's been kind of just magic of just like, oh, somehow my computer knows how to get to google.com. And we know how to map the IP address to that DNS, look up the host name to IP address. But once we get the IP address, how does it know to get from one computer in Provo to another computer in San Francisco or something like that? How is that done? And so that's done in the network layer. So there's two key functionalities that the network layer provides. And we're going to go high level for now. So first is forwarding. This is taking a packet in as a router and then deciding what output link. Where should this go? Should it go to output link 1, 2, 3, 4? Depends on the router how many output links it has, but it's going to decide what to do with that. Now, you have a router at home, most likely, right? A wireless access point or wireless router. Its forwarding is really simple because it only has two options. It has the routing that it does from within your network, or it just sends it out to the internet. So, but you can think of more complicated routers where it might have multiple places it can go, not just either in your home or in the network, but maybe multiple parts of the internet. And so that's the job of forwarding. Then you have routing. Routing is, how do I get from one point to another? And so that's done through routing algorithms. So there's kind of a nice analogy that helps illustrate the difference between routing and forwarding. You can think of forwarding as like, I'm driving down the road, I'm a car, right? I'm driving a car, so I'm like a packet of data. I decide, okay, do I take a left at this light, or do I take an exit here at this intersection, freeway exit, or do I get on the on-ramp? Those are all very local decisions that happen as the packet goes through these different intersections. Whereas routing is more the process of like planning out your trip. How do I get from point A to point B? There's a lot of forwarding that happens along the way, but at the end of the day, that's a routing job of like, okay, this is the general place you should go, the process of planning out your trip from the source to the destination. So there's Google, has some algorithm to decide what the fastest path is for you to, get from point A to point B. Routing algorithms have the same kind of thing. They're a process of how to get a packet as fast as possible from one point to another. Okay, so let's get into a little bit more depth of what this data plane versus control plane is. The data plane is this local per router functionality. It's where the forwarding happens, where a router gets a packet of data, it looks at the header, and based on the headers, in this example, it's seeing a 0111. It says, okay, if I see that, that means I need to send this data over, my output port 2. So that's forwarding. So data plane is all about forwarding data. Whereas the control plane is, well, how do we notify every router how it even knows to send out a port to? How does it even know that? That's the network-wide logic. It's the sub-communication that's going on, the control plane communication on between routers that help them update their tables and understand how to get data from one place to another. There's two different ways of handling the control plane. The traditional way, where we have routing algorithms that are distributed between all nodes. And then we have a software-defined networking. That's relatively new, SDN it's called, where you have one node, one central entity that's controlling all these different routers. And we'll talk about that. I have a picture on that in a second. So it's per router control plane. Let's talk about that. So we have a packet coming in. Let's cut open these routers. That's what it's trying to show. Cutting them open. What's inside of these routers? What's inside is some kind of forwarding table. So when I see a header like this, I send out port 3. If I see a header like that, I send out port 2 and then 1. So that's our forwarding going on right there. I get a packet and I look up at my table and say, okay, cool. In this case, it's port 2. Done. And move on. I forward it out and I move it on. But how did this get populated in the first place? So there's this routing algorithm. So there's this communication between these different routers. Now they're not communicating data to each other. They're communicating control messages to each other. That's why it's called the control plane, because they're sending messages. Even if there was no data being sent between these routers, they'd still be sending messages to each other to update this forwarding table, to communicate with this routing algorithm. And then this routing algorithm is what influences this forwarding table. So that's the data plane is below. It's hey, I got some data, look up in the table, forward it along. The control plane is what messages do I send? What information do I need to keep track of to do a good job of forwarding this or of routing this data from one place to another that is the least cost. So that's the control plane. Now, just to give you, we won't talk about it much. This is pretty much only a slide, I think, on software-defined networking, SDNs. But just to give you a kind of a flavor of what those look like, cut our routers open and look inside. We got something different going on now. So we have this central controller going on, and it can be a group of computers. It doesn't have to be one computer, but some kind of central entity that keeps track of all the logic, the remote controller, and then its job is to update the routing table, the forwarding table of each router. And so this is really nice because it lets you do some interesting things, lets you have a better, more global view of what's going on. This is really popular in cellular networks. Cellular networks want to have really fine control over their networks. They want to know how much data is passing through so they can charge you money. They want to differentiate different users, roaming users versus non-roaming users. And so they want to have kind of this nice global remote control capability to put logic on each one of these routers. So the routers are still fast. It's not like they send the data up to these remote controllers. That would be way too slow, right? To every router to pass the data up. But what this lets us do is have one entity that controls all the rules about what each router does, and then the router still does the normal, really fast forwarding process. But we can update those on the fly through one central entity rather than it being a distributed algorithm like the previous slide was. So once again, this is the data plane, is the controlling. These CAs is controlling agent. That's what that stands for. So there's some software running on this device that receives messages from the remote controller and then updates the routing table. Okay, so that's kind of what's inside a router. Let's talk about what services does the network layer provide. I think every layer we talk about that. So what services does it provide? Now these are examples of services that could be provided, and there's different ways to think about this. There could be at the datagram level, like at the individual packet, we could ensure guaranteed delivery, or we can ensure guaranteed delivery with a certain amount of time. That's one option. Or you can think of this more from like a flow of datagrams. Saying, oh, okay, well, we'll make sure the data is in order, or that there's some minimum bandwidth for that flow. Those are all possible services that a layer such as a network layer could provide. But as we've alluded to in past lectures, that's not quite what it does. The internet is what we call best effort. That's its service model, which means it provides no quality of service guarantees. QoS is the short term for that, quality of service. It provides no bandwidth, no loss, no order, no timing. It provides nothing. So just make it a little bit more clear, if I'm not clear enough, there's no guarantees on the in-order delivery, the timing, the bandwidth available. It's just going to try its best and hopefully you'll get the data there. That's an interesting design decision. Why did we choose to design the internet like that? Because there are other protocols out there, ATM being the big example, but there's even ones that are on the internet that do provide this guarantees, and that's really nice. You then wouldn't have some of the issues that we have become accustomed to in the internet. Things like, buffering of video, or, when Zoom kind of skips for a second, or, there's this weird latency issue sometimes. That's all because of best effort. If we had constant rate, maybe the rate wouldn't be very good, but at least it would be constant. We'd be guaranteed to have that. So let's talk about this best effort kind of service idea a little bit more. Why do we do that? I think the biggest reason is simplicity. Simplicity allowed the internet to grow to the scale that it has, because now we don't need to have all this heavy machinery. I don't really mean machinery, I guess I mean more like, software or hardware, big buffers or whatever, or lots of acknowledgements back and forth. We can keep it really simple, and we can push all the complexity to the edge of the network. We've also had the blessing of the bandwidth has just kept on growing and growing as a result. And so these real-time applications that we've been more accustomed to using work well enough because we have so much bandwidth available to us. If it was really minimal, then these would just be not very good. And so they work good enough most of the time, right? Good enough is what I like to say with the internet. It's hard to compete with that when you have the simplicity, and it works pretty well most of the time. And then we also have this idea of kind of the CDN idea, content distribution networks, of, well, what if we just replicate our data and push it closer and closer to the edge? Then it becomes less required to have these guarantees, and then our bandwidth becomes what we depend on. And so that's another reason why it's worked. And then we have these elastic services. So the congestion control, elastic services means things that can grow and shrink with the needs of the network. That's been really helpful for us, because we tend to not need consistent throughput for long durations of time. Usually we just burst out, need some data, and then we get it back. And we don't need, it can grow and shrink as needed. So as we're shrinking, someone else can be growing, and that kind of just generally works out pretty well on the internet. And once again, it's hard to argue with the success. I mean, the internet's pretty darn popular, and it's best effort, so it's worked well. I think, we could probably think of better ways of doing it, but would it scale as well? Would it be as simple? I don't know. So that's, internet's worked really well. Okay, let's dig a little deeper into what's inside a router. I just actually only have a few slides on this. I wanted to kind of tie up some loose ends we had talked about in previous lectures. I guess before we do that, let's talk about longest prefix matching. This is a really important concept that you need to understand for how a router routes its data, or forwards its data, I should say. So longest prefix matching is when I'm looking at an address, a destination address, and I look up at my table, how do I match it up? I can't have a one-to-one mapping for every IP address there's an output port, because there's a lot of IP addresses out there, right? So 2 to the power of 32 to be exact, IP addresses. So I don't want to have a table with all those in there, right? So I want to kind of have some sparsely populated table that doesn't have every single entry in it. And so if I have an IP address, how do I know which one it matches with, what entry in my table? And so we use the longest prefix matching. The address that matches the longest part of our address is how we'll decide where it goes. So let me be a little more clear on that. It helps to have a picture. So here we would say, hey, these are the entries in our table. We have 4 entries, 3 specific and then anything else we don't know about, which is often called our default route. Well, let's go to port 3. If we don't know what it is, just send it on port 3. But if we do know, then we'll go over port 0, 1, or 2. So here we have an IP address, but notice we have these stars here. That means like wildcard. We can anything there we want. And so you can kind of think of this. I mean, we know a little bit. You can do like what's it called, like geo, lookup of your IP address, and that's because IP addresses have some degree of locality to them. And so that's what we're capturing here is we say, well, I don't know what these ones mean. I don't really care. But if it starts with this right here, then I need to send it this direction. So maybe, this is over in the East Coast, or this is West Coast, and then this is Utah. And so, you might kind of start to say, hey, go over there. And as it gets closer to where it needs to go, those routers will have more specific information about where those need to go. So here we only have one address that's a little bit more specific. The rest are pretty vague in terms of the IP addresses. So let's say we get this IP address. And we haven't talked about IP addresses yet in detail, but you should have some familiarity with them. This isn't obviously in the binary form. So we look up in our tables, but none of these, these match this IP address specifically. But we see one that starts with that. I think this one right here, the top one, starts with that. So you say, okay, this goes out port 0. It's a match. Great. But then we look at this one. Let me go back. Let me look at the second one. We say, look, it matches the bottom one, but it also matches this middle one right here. So which one do we choose? That's where the longest prefix matching comes in, is because we have more specific information about this address and it matches, we will choose port output link 1. So here it matches, yep, it matches, but so does that one. And that one matches more, more specifically, or longest prefix. So we'll send it out that one. So that's longest prefix matching. You'll want to be familiar with that term and understand what its implications are. We talked about earlier on in the semester about how big do you make the buffers. There's a test question on it. Do you want to make them really big or really small? I think, let's go through that thought process. So here's just an example of what size you actually do want it set to. We never actually captured what you should set it to. We didn't have quite enough information at the time. You want to set to the round trip time times the capacity divided by the number of flows. Now, this is a lot of guessing, right? You can measure pretty well what the round trip time is because you're constantly measuring it. You know the capacity, but the problem is you don't know how many flows you're going to have any given time. So you can guess, or you can have historical data to know roughly what that should be, and that's what you set your buffer to. And of course, we talked about this already. If you have too much buffering, then you increase the delays, and that's not great. You have like sluggish TCP responses, so we don't want to have it be too big. So how do we manage this buffer? And I tell you this just because I find it interesting. We're not going to know very much information about this. Just kind of give you a broad idea of, well, when there is a queue that's full, how do we manage that? So here we have our queue of packets arriving. This is our link. So we're going to send it out there. So this is the queue of the router right here. So how do we deal with this when a buffer gets full? Do we do a tail drop? So we just say, okay, like, oh, you're at the tail. You were the last one in, so I'm going to drop you. Do we do some kind of priority? Say, oh, this packet's more important than this packet. How do we decide that? Do we mark them? That's the example. There's a lot of research in that, where we mark certain packets based on certain characteristics about them, and then we mark the packets that are, if it gets full, we delete the packets that are marked. So that way we kind of randomly distribute the lost packets across lots of different flows or types of data. So just give you a little feel on how to deal with this. There's a couple of different approaches. First come, first serve, priority, round robin, and weighted fair queuing that I want to talk about. So first come, first serve, or first in, first out is example of kind of the simplest packet scheduling, where if you're the first one, you get head of the line, and then as it gets full, you get dropped if you're the last one in. So nothing crazy about that. Let's move on to the priority scheduling. So here we might have two queues. Say, oh, we have the high priority queue, and we have the low priority queue, and this link will always service the high priority queue if there's anything in the packet. So as we get some data come in, we have to decide, well, what is its priority? And then put it into one of these queues. And that could be based on IP address, based on what type of class of data it is. In IP headers, there's a little bit of information about that. We'll talk about that more when we get to the header. So that's one way to think about this problem, is have multiple queues. Maybe it's not actually multiple physical queues, maybe it's all done in software, but you can imagine that, from a logical standpoint, there's multiple queues, and we decide which one goes in there, and the low priority only gets handled if the high priority is empty. It's still maybe first come, first serve. So if somehow the high priority does overflow, or the low priority overflows, those would get lost, but you could add like some kind of priority classes. So just kind of highlight how that looks in time. So here we got time going across horizontally. Packet 1 arrives, and then packet 2 arrives, so we're servicing that's in the queue. And then when it departs, so it's packet 1 departs, because packet 3 has higher priority. We're assuming these red are higher priority. 3 gets serviced next, and 2 has to wait in another queue. 3 gets serviced, and then finally there's no more high priority queues, high priority packets. So we send out 2, but maybe while we were sending out 2, we sent out 4. So then 2 gets sent out, then 4 gets sent out next, then 5 by itself. So that's an example of priority queuing. Then there's this idea of round robin, where maybe we still classify our data, but now we don't have to have high priority, low priority. Maybe it could be, oh, this is video, this is web traffic, and this is some other background traffic. And so what we could do in the round robin approach is we don't give priority to one or the other. We just say, okay, we'll start with red. We'll send out 1 red, and then 1 green, and then 1 purple. And then we'll go back up in a round robin style and say, okay, red, green, purple. It's that way. What that's providing is we are prioritizing each class of data, but we're equally sharing each class of data, I should say, not prioritizing. We're equally sharing each class of data, but we're not prioritizing one over the other. So that way I can make sure that all my video streaming data comes through, but also my web traffic comes through, and also that. So if there's tons of video streaming data, that might get overflowed, but it won't take over my flow of data with all this other traffic. And so it just goes around in a circle, hence the round robin. Then of course we can add some weighted fairness. It's called weighted fair queuing, where we add some priority to these. We add some weight to it. So we say, hey, let's send out 2 of the red for every 1 green and every 1 purple that we send out. And so that's a way to then add some priority on top of these on a per traffic class. This brings up an interesting point, and unfortunately this doesn't really work very well in a recorded video, because I would love to talk to you guys about what it means, what neutrality means to you, and what you think are interesting. So hopefully I'll remember, we'll have a discussion about this in class later on, because I find net neutrality to be really interesting. But so net neutrality is how should an ISP or anyone that's part of the internet, how should they allocate resources for different types of traffic? And so we see that the technical side of that is like, well, what packets do I schedule, or whose data do I put in the high priority buffer? So that's the kind of mechanisms for how net neutrality is administered. But the kind of the idea is like, well, should I hide free speech, encourage innovation? So the kind of example I like to use is back in the day, I don't think this is a thing anymore, but maybe it is, where T-Mobile offered a service where he said, hey, you have a data cap of a certain amount of gigabytes of data a month, but if you stream Netflix, we won't count that towards your data cap. So that's not net neutrality. That's the opposite of that. That's saying, hey, we're going to treat Netflix special because maybe Netflix paid T-Mobile a lot of money, or maybe vice versa. I don't know the economics of it, but that's treating data as different depending on where it's coming or where it's going to. And that's administered through these packets, through these buffers and stuff like that, but it has huge implications, I guess, and especially with encouraging innovation and competition. Because let's say I want to start a video streaming company. I can't compete with Netflix. I don't have the money to pay T-Mobile to prioritize my data. And so now are we stifling competition or innovation by by not having net neutrality? The idea of net neutrality is keeping the internet as a dumb pipe, is what we call it. Where there's no nuance of, okay, well, if this traffic's going over here, I need to treat that differently, or it's coming from somewhere else, I'll treat that differently, or it's video data versus other data. Like, no, all data should be treated equally. There's no special data or important or less important data. It's all just data at the end of the day. That's the idea of net neutrality. We keep everything neutral. And there could be arguments for both. I tend to be more on the pro of net neutrality. I think data should just be treated as data, and that we shouldn't give any special priority to other things. But there are arguments for treating certain data in certain ways. And it has big implications, though, for things like freedom of speech. You might not seem like that, but what is it called? The Great Firewall of China. I don't know if you've heard that before. China has a big firewall around their whole country that will limit certain things. You can't go to google.com in China because you have to use their equivalent of Google. And so that's a way, maybe that is a way to stifle free speech. I don't know. I don't know the politics of that kind of stuff, but that's something that, could happen when we start treating data differently. Okay. Well, that's it for this lecture. I wanted to keep it kind of short. I don't think I succeeded in that, but in the next one, we'll talk about IP addresses. Thanks for joining in.